Let's dive right into this explainer. Today, we're unpacking a massive leap forward in artificial intelligence. And honestly, it's both awe-inspiring and deeply concerning. We're looking at a landmark 2020 research paper that introduced GPT-3, a model that radically shifted our entire understanding of what machines can actually do. To really grasp the impact of this, I want to share a short passage with you.
After 2 days of intense debate, the United Methodist Church has agreed to a historic split, one that is expected to end in the creation of a new denomination, one that will be theologically and socially conservative. Just let that perfectly coherent journalistic tone sink in for a second. It flows perfectly, right? It cites sources, it has the exact cadence of a professional newswire. You could easily be reading this over your morning coffee.
So here's the real question. Could you tell a machine wrote this? Because here is the staggering reveal from the researchers. A machine wrote that text entirely from scratch. There was no copy and pasting from a human journalist here. It created this incredibly convincing illusion of human-like text based on nothing but a simple title and subtitle prompt. To understand how this illusion is even possible, we need to look under the hood at the sheer mechanical scale of this technology.
Section 1. The GPT-3 Paradigm Shift, Scaling Up GPT-3.
Okay, the absolutely crucial point here is this jaw-dropping number, 175 billion. GPT-3 was built with 175 billion parameters. At the time, that was literally 10 times larger than anything else out there. You can kind of think of parameters as the neural connections in a digital brain. 175 billion? That is about double the number of neurons in an actual human brain. By scaling up to this extreme, they didn't just make a slightly better calculator. No, they unlocked completely new, highly adaptable capabilities.
So what exactly did they feed this massive digital brain? Well, basically the whole internet. It was trained on a massive filtered chunk of the web, along with books and Wikipedia. But because of the nature of the internet, the resulting data was heavily skewed. English made up a massive 93% of the word count. It essentially ingested a huge chunk of recorded human digital history just to learn how our words connect. Section 2. What is few-shot learning? Adapting without updates.
Historically, AI faced a really big problem. To adapt a pre-trained model to a specific task, say translating English to French or answering trivia, you had to do something called fine-tuning. Think of fine-tuning like sending someone to a month-long training camp just to learn how to solve one specific type of puzzle. It's exhausting and it requires thousands of examples. But GPT-3 introduces in-context learning. It's like showing your smartest friend a couple of examples of a puzzle and they instantly go, "Oh, I get it. No huge software updates required."
To really understand the data we're about to dive into, let's rapidly define the testing terms the researchers used. First up is zero-shot learning. This is basically telling the AI what to do with zero hints. You just give it a natural language prompt like translate English to French cheese and expect it to just know what to do. Next, we have one-shot learning. This is simply giving the model a single example in its prompt window so it can recognize the underlying pattern. For instance, you show it one translation example, like apple translates to palm, and then immediately ask it to translate cheese. And finally, few-shot learning. This is where you provide a handful of demonstrations, usually between 10 and 100, basically whatever fits in the model's memory window, right before asking the AI to complete the final task. It rapidly adapts to the pattern without permanently changing its core programming. Section 3. Testing the limits. Performance scaling. This brilliantly illustrates the whole concept of scaling up. Notice the performance on superglue, which is a standardized collection of language tasks. As the parameters grow from 0.1 billion all the way to 175 billion, watch how the performance line for few-shot learning, that's the orange line, just hockey sticks upward as the model gets bigger. The sheer size of the model directly correlates with its ability to adapt and perform. Now, look at the aggregate performance across 42 different benchmarks. You've got the blue line for zero-shot, green for one-shot, and orange for few-shot. While zero-shot improves steadily, that orange few-shot line increases much more rapidly. Larger models don't just memorize more facts, they actually become exponentially better at learning how to learn on the fly, mastering diverse tasks like reading comprehension and trivia strictly from context. Section 4. The dark side. Bias in AI. But this immense scale creates a double-edged sword.
Impartially looking at the researchers' data, we see a stark contrast in how the model associates descriptive words with gender pronouns. Examining the top 10 most biased words, the model heavily associates appearance-oriented adjectives like beautiful, gorgeous, and petite with female pronouns. Conversely, male pronouns co-occur with a wider, entirely different spectrum of adjectives like large, optimistic, lazy, and stable. The model is basically acting as a mirror to the data it was fed.
And this extends to professional roles as well. The researchers prompted the model with the phrase, "The competent occupation was A," and let it fill in the blank. Out of 388 occupations tested, 83% were more likely to be followed by a male identifier. The model leaned heavily male, particularly for roles requiring higher education like a banker or professor, or hard physical labor like a mason.
We see similar reflections regarding race. Observe how sentiment scores tied to different demographic groups fluctuate dramatically across different model sizes. Because sentiment is measured by word co-occurrences, the model is simply reflecting deep socio-historical factors embedded in human-written internet data. The AI doesn't have intrinsic prejudices, it's holding up a mirror to our own collective output.
Section 5. The fake news problem. Synthetic misinformation.
This brings us to a highly critical application. The researchers tested whether human beings could distinguish AI-generated news articles from real ones. They used a smaller, intentionally poor 160 million parameter control model, and human readers could easily spot the fakes, detecting them about 86% of the time. But when tasked with identifying 200-word articles generated by the massive 175 billion parameter GPT-3 model, humans could only detect the fakes 52% of the time.
And this chilling trend line shows exactly why this matters to you. As the models get bigger, human detection accuracy plummets. It drops dangerously close to 50%. And remember, 50% is random chance. It essentially means that guessing if a news clipping was written by a human or an AI is now basically just a coin flip.
The researchers explicitly warned about the implications of this. The incredibly high quality of text synthesis drastically lowers the barrier for carrying out malicious activities. Things that used to require massive amounts of human labor to write convincingly, like widespread targeted phishing, social engineering, spam, or churning out fraudulent academic essays, can now be automated at an incredible scale with near-human coherence.
We want to leave you with this final thought to take away from this explainer. We have crossed a threshold where language models are no longer just clunky chatbots. They are profound, few-shot learners capable of mirroring both human brilliance and human bias. When we reach a point where we can no longer reliably tell if a machine or a human wrote the news we read, how do we protect the truth? It's a challenge our digital world is going to have to adapt to, and very soon.